Welcome to this pre-class lecture on optimization problems. As you can hear, my voice is not my usual one. That's not because there is someone else recording, but because I've got a pretty bad cold. However, you still need to find this information, so I'll do the best I can, and hopefully my voice will not be so mumbled that you will not understand what I'm saying. Fortunately, however, optimization problems at this level should be a fairly short topic in that you have already seen them before. You certainly have a lot of experience with them, or let's say some experience with them, and therefore what I'm going to do in this lecture is just to highlight some important aspects of optimization problems, some key ideas to keep in mind when you address them, and then we're going to spend time in class just going through several examples of optimization problems and working through them in a lab type setting. So hopefully the practice will bring up a number of issues that will address your own difficulties, your own problems with optimization problems, and will be able to develop further your ability to solve problems. Now, first of all, what is an optimization problem? I like to start with this image of money because one of the most common applications of optimization problems is to try and use the mathematical methods of calculus to figure out under what situation we can make some kind of financial venture as profitable as possible. So, for instance, how can we produce certain items so that the cost will be minimum, or that the revenue will be maximum, or even better, the profit will be maximum. This applies to the producers as well as to the sellers. So how much should a store charge for an item in order to get the maximum profit, and so on. But there are of course other applications. Another typical one, another classical one, is the one which involves fencing, and it usually goes like this. You have a certain amount of land that you want to or you want to enclose a certain amount of land with some fencing, and you want to do it in such a way as to use the minimum amount of fencing so that it will cost as little as possible. Another typical application is that of how to cut a piece of cardboard of a certain dimensions so that once folded it will produce a box which is as big as possible. Again, we're trying to make it as big as possible. Probably you have seen this kind of problem before. Or another one, for instance, might be how do we fold a piece of dessert, or a piece of whatever you call that thing that you fold to make an ice cream cone, in order to make a cone which has the biggest possible volume so that it will hold as much ice cream as you need. So more generally, or more technically I should say, an optimization problem is a word problem, so that means you'll have to build up your equation. Remember, a word problem is not identified by the fact that there are words, but by the fact that you have to build up an equation, in this case actually a function that you will have to then use in order to identify where the maximum is. So this is a word problem in which we're going to have one dependent quantity related to one independent variable. Okay, so we have an independent variable that can be decided upon, and a dependent quantity which is the thing that we want to optimize. So the goal is to choose the value of the independent quantity that will make the dependent quantity largest or smallest within a certain acceptable domain. Now, this last sentence is a little bit longer than my usual sentences here in these lectures, but that's because I couldn't make it any shorter. Each word or each expression in there is important and needs to be taken into account. So you may want to reread it and make sure you understand each piece of that sentence. So that is the goal of the optimization problem. So what we want to do is we want to find the value of the independent variable that makes the dependent variable as large or as small as possible. If that sounds familiar, that's because what we're asking for is looking for the maximum or the minimum of a function. So you can already see that first derivative analysis and identification of max and mins will be very, very important, and all the things that come with it. Now, here are some strategy tips for optimization problems. So when you're attacking an optimization problem, what kind of strategy should you keep in mind, because they might end up being useful? Well, first of all, what you want to do is you want to express the dependent variable as a function of a single independent variable. Now, you might say, well, you just said that it was supposed to be a function of an independent variable. True, but sometimes the information given in the problem, in the wordy part of the problem, gives us a way of describing the dependent variable as a function of several independent variables. And so what we need to do is we need to get rid of some of them. Okay? So if there are other variables, then we need to eliminate them by looking for and finding some suitable relationships which will allow us to write all the other potentially independent variables in terms of one only. And then, after we've done that, then we end up with, as I said, just a first derivative analysis. All we need to do, excuse me, all we need to do is use the first derivative analysis methods. So identify all the critical values and then put those ones and the values for which the function is undefined, put them all on a number line, and then find where the function is increasing, decreasing, and so on. And that will tell us what are the possible max and mins, and from then you can figure out which one is the one that provides the solution for the problem. Now, notice that in general, an optimization problem will have some practical restrictions on the domain. So only certain values of the independent variable are possible. For instance, we don't want negative lengths or negative volumes or things of that sort. Or maybe if we're trying to optimize our investment, well, there is only a certain amount of money we can invest, and therefore there is a maximum to how much we can do, even though mathematically we could go beyond that maximum. So make sure that the optimal values you found are always within those practical restrictions, or which is an equivalent way of saying that. Make sure that you do your first derivative analysis only within the given acceptable domain. Don't go outside of it. And finally, let me give you some technical tips for optimization problems. Some tips that at this stage may look like little details of not much importance, but you'll be surprised how much they can affect your ability to solve or not to solve, get stuck with a word problem. So, first of all, remember that a critical number may be a maximum or a minimum or neither. So finding the critical numbers is not enough. What you need to do is you need to then classify them. You have to find out for each of them whether it is a maximum, a minimum, or neither. And if it is a maximum or a minimum of the type we want, is it really the best one, or is there a competition among 2 or 3 possible ones? Another thing to remember is that the required optimal value may occur at one of the endpoints of the acceptable domain. Remember, when your function is defined over a closed domain, a closed interval, then the endpoints are also critical numbers, and you don't want to forget them in the analysis, because that's exactly where the best solution of the problem may be. It may be that you have to go all the way in one direction or the other in order to obtain the best results. Remember also that in a word problem you have to build up the equation on your own, which means that you have to use appropriate formula. Make sure always to look up a formula that you need rather than guessing. And this goes both when you're trying to write down the dependent variable in terms of the independent one, or when you're trying to eliminate additional independent variables by relating them to the one that you want to use. Either way, make sure that the formula you're using are the proper one. If you're not sure that it is a correct equation or a correct formula, go and look it up. Finally, again, the usual thing of using letters to denote variables, but using the actual numbers for any constants. Okay, so remember, at some point we have to do a first derivative analysis. We have to take derivatives, and we have to make sure that we're not going to take derivatives also of constants, but we're also going to want to make sure that we're going to take the derivatives of variables. We're not going to consider them as constant and send them to 0 in the differentiation process.